Good morning, everyone. I welcome you all to our one-day user training program on mw2mech, a software package combining microstructure modeling and mechanical property prediction. So let me quickly give you the brief overview of what we have planned for today. Our workshop is divided into theoretical and practical sessions, and each session will be interactive and engaging with opportunities for questions and discussion. We will be starting with the introduction, where we will explore mw2mech and mw2mech key concepts, followed by the demonstration session, where we will learn the usage of mw2mech and OOF2 with some test input data sets. And we do have the hands-on session to reinforce learning and practical use of mw2mech and OOF2 software. We will engage you in hands-on case studies. This activity will allow you to gain hands-on experience with mw2mech and OOF2. This in turn may be useful for your research or the project work or further development of mw2mech or OOF2. Lastly, we will have a question, answer and feedback session. Your active participation is the key to the success of this workshop. We encourage you to ask questions, seek clarification and share your insights throughout the day. We have also set aside time for a dedicated question answer session and welcome your feedback at the end of the workshop to help us improve future sessions. We will recap the key takeaways from the workshop and discuss the next step during the conclusion and the next step session. Let me quickly give you the brief overview of the key speaker of the today's workshop. He is one of the PI of the mw2mech software, Dr. Rajdip Mukherjee. Dr. Rajdip Mukherjee is currently working as an associate professor in the Department of Materials Science and Engineering, IIT Kanpur. He obtained B.Tech degree from Calcutta University and went on to complete his master's and PhD degrees at Indian Institute of Science, Bangalore. Prior to joining IIT Kanpur, he gained experience as a postdoctoral researcher at Karlsruhe Institute of Technology in Germany. Dr. Mukherjee's research focuses on microstructure modeling and simulation to investigate pattern formation in thin films, the impact of external fields on microstructure evaluation, and the evaluation of microstructures in superalloys. His research methodology involves utilizing phase space models, multi-scale models, and machine learning techniques. I welcome Dr. Rajdip Mukherjee and thank all the participants over here. Over to you, sir. I request you to start with the session.
Okay, thank you, Ms. Agarwal. I am Rajdip, and I'll start the the technical sessions for the workshop. So should I share the screen, right? Screen window and enter screen.
Sir, let us wait just for 5 more minutes. It's
5 more minutes, okay. Should I just share the first, or I check the screen sharing is not working or not?
Yes, sir.
So just check whether it is working or not, the screen sharing. Is it working?
Yes, it's visible here.
It is visible, right? Okay.
Yeah.
Okay, good. So I'll
Sir, we are not able to hear you. Are you speaking, Rajdip, sir?
Yes, yes. Can you hear
Yeah,
me?
now. Yes, yes, yes.
Yes.
Sir, we can start.
Okay, thank you. So good morning, all the participants. I am Rajdip Mukherjee from Indian Institute of Technology, Kanpur. Today we are going to start a workshop on μ2mech, a multi-scale approach for microstructure simulation and mechanical property prediction software package. So this is a one-day workshop, user training workshop on this material science and computational chemistry software, and this is organized by CDAC. So this software is part of the project, National Supercomputing Mission project, where me, Rajdip Mukherjee, and Professor m2mech and Professor Kaushik Das from Professor Kaushik Das from IIST Shibpur, we are involved in this project, right? As a part of this project, we have developed this software for microstructure. So microstructure evolution and mechanical property prediction. So as the name suggests, you can see the mu, that is the mu stands for micro, right? Microstructure. And microstructure to mechanical property prediction, right? So here we'll demonstrate a software, and also you'll get some hands-on training on how to simulate the microstructure evolution with time for an alloy system using this software, and how we can export this data to a open source software which can predict the mechanical property prediction. So you can also later on, this microstructure evolution can be exported to other softwares like Abacus or other things. But today we'll mostly discuss how it can be exported to a software which is open source software which can do mechanical property prediction, and how mechanical property prediction can be done using that software, that we'll also discuss. So is it not moving? 1 minute. Yeah. So the students contributed in this project are PhD students, mostly PhD students of Department of Material Science and Engineering, IIT Kanpur, and Mr. Albert Linda, who developed the graphical user interface responsibility for all the modules that working properly in this software. So he's the main person in this development of this graphical user interface based software. Mr. Vishal Panwar, he is also a PhD student in our department, and he is working on the mechanical property prediction prediction thing, and he mostly works on this OF2 or Abacus, these kind of things. When you have a microstructure, how to predict the mechanical properties. Mr. Ankit Singh Negi and Rupesh Safle, they worked mostly on the background code that is important for developing this phase field modeling tool. And Ankit Singh Negi, he is also a PhD student in our department. And Rupesh Safle initially started this work, but he is now doing postdoc in Helmholtz Institute in Germany. So in this project, mostly these 4 students, these PhD students, they developed this software. Is there any noise? Develop this software, right? So this is a brief outline, although you know the schedule. This is a brief outline what we are going to cover throughout the day. So now I will give you a 1-hour lecture on our theoretical background of μ2mech, which is the introduction to μ2mech. And this μ2mech is based on the phase field modeling for microstructure evolution. So I'll give you some example of phase field models for microstructure evolution. And the solid solution model for alloys, that is also important because unless you know the how different atoms of different elements interact with each other to form the Gibbs free energy, then it is not possible to predict the microstructure. So this is the thermodynamics part that also we are going to discuss. This is a mostly textbook part. That is what we are going to discuss, right? So this will form the basis of the μ2mech, right? In the lecture 2, after an hour, there will be a half an hour lecture. by Professor m2mech, where he will discuss mostly multi-scale modeling, density functional theory simulation for elastic constant calculations for next and half an hour, which is also important for the software development. In the afternoon session, we have two demonstration session, and one of the first demonstration session will be conducted by Mr. Albert Linda, who will demonstrate the m2mech software for microstructure modeling using OF. This is not OF2, sorry, this is using, so this is the m2mech software he will demonstrate. And so this session is very important, where you will get most of the essence of the software, how to use defined modules of this software that you will know, right? So this demonstration one is very, very important. Please ignore this OF2 because this is for the second part of the demonstration, right? So the second part of the demonstration will be conducted, 1 hour demonstration will be conducted by Professor Kaushik Das from IIST Shibpur. He will discuss the elastic and elastoplastic property prediction once we get the microstructure from OF2, right? And and then we'll go for a hands-on session where we'll give you some kind of task based on the demonstration one. So we are planning the demonstration one, we'll use an alloy system, which is iron chromium alloy. But during the hands-on session, we'll give you another alloy system, which is iron copper alloy, where you have to do similar stuff which is shown in demonstration one. So the hands-on session will only cover the m2mech part, but not this object-oriented finite element thing. That is the demonstration 2 related thing. That is the open source software. So mostly how to use the m2mech software, right? That is which predicts the microstructure and export the microstructure to a open source software for elastic and elastoplastic property prediction. And finally, we'll have a question answer and feedback session, and we request you to actively participate in this session. Okay, so there is some problem with, okay. Yeah, so in this work, we have developed a multi-scale modeling software, m2mech, combining atomistic and phase field simulations for microstructure modeling during solid state phase transformation, followed by microstructure-based prediction of mechanical properties using finite element method, right? And that is the OF2, right? So these are some of the snapshots for graphical user interface for simulation of mineral decomposition, which we'll learn today how to use this software to simulate mineral decomposition, right? Which also I'll discuss in after next few slides. So this is a kind of phase transformation which is very important, metallurgical phase transformation. Also, you can see this kind of phase transformation in polymers and glasses as well, right? So I think some of you are from physics and chemistry background. Some of you may be from the metallurgy background. So some of you may be familiar with this kind of phase transformation. So next up, I am showing you a few online resources. This will be shared with you after the after this workshop. So this is the first one is the GitHub link where we have the so this is the open source software, as you know. So you will get the source code for this m2mech, right? So there is a background C code there, which is for phase field modeling. And see all these source files for m2mech, because m2mech, you will see the front end is a graphical user interface, but back end there is a program which is running, which is a C program which is running, which is solving mostly the differential equation related to the phase field modeling, right? And that those codes will be available in github.com, and also the installation procedure. It is already installed in Param Sanganak, but you may want to install it in your own laptop, which has a Linux system or Ubuntu or CentOS. So you can directly download from this GitHub link, and then you can install it in your own desktop as well. Okay. And then there is a I'll provide you a link of a paper which we published, which is a m2mech, a software package combining microstructure modeling and mechanical property prediction. And this paper contains all the screenshot of the softwares, how to install it, what are the basic algorithm that we have followed in this software, the example of iron chromium alloy, how we simulated this thing, how it can be exported to a OF2. All these things will be part of this paper, which is published in Physica Scripta, and it can be downloaded from this link. Okay, so this can act as a manual kind of thing for this software, right? So it contains all the details of this software. The DOI will be also given, right? So this slide I'll share with you. And then so now we'll start with this software, the background of this software. So in this talk, in the first 1 hour, I'll not go exactly into the more details about the software, but what actually the software is doing, or what are the theories, or what are the computational tools you need to know, which is basically responsible, which is running in background of this graphical user interface. The demonstration part will be in the afternoon session, where you will see how to use this software. But it is important to know what actually the software is doing, right? How it is able to simulate the microstructure, right? So what kind of computational tool we are using, and what exactly we are interested to do in using this software. So if someone has any question in between, you can interrupt me, and you can also ask. Okay, so that is possible. Okay, so please let me know if you have any doubt in between. You can ask me any question. Okay, so we start with a basic slide of a multi-scale modeling and simulation. This is important because here we are connecting few, although it is mostly the phase field modeling software, but it is connected with the atomistic simulation as well as the finite element software, right? So here you can see a plot where you can see the x-axis is time and y-axis is the length. And in this time and length scale, a defined time and length scale, we have defined materials problems, right? And for these problems, like in experiments also, you have defined kind of microscope, like right, optical microscope, scanning electron microscope, transmission electron microscope, then you have atom probe tomography. They have defined resolutions, but all of them are very important, right, at defined length scales. In computations also, we have defined computational tools like density functional theory. Um, are you audible? Am I audible, Ms. Agarwal?
Yes, sir. Yes.
Yeah, yeah. So first is the density functional theory, which works at a very lower length scale, where the electron structure calculation and all these things work here. People use the density functional theory, like in a graphene related simulations, it is also used in DFT. Then you have kinetic Monte Carlo and molecular dynamics simulation. These are called atomistic simulation, where the system is described in terms of atoms. Then there are simulations which are in mesoscale. Mesoscale means it is nanometer to micron scale, right? And in nanometer to micron scale, we have mostly the problems which are related to microstructure evolution. And why microstructure is important? Because microstructure ultimately tells you what will be the macroscopic property of the system, right? So it is very important to know what is the microstructure for for a material. Then we can predict what will be the property. So if we can tailor the microstructure, we can also predict the property of that alloy, right? So there's the phase field modeling, cellular automata. These are some of the continuum modeling tool which is used for in the mesoscale regime for microstructure modeling and simulation. Then there is a model which in mechanical engineers mostly use, is a finite element model, which is used for property prediction. Property prediction, mostly mechanical property prediction. Although the microstructure is important to understand mechanical properties and other functional properties as well, like magnetic properties, electrical properties, all these things. But finite element modeling is one of the uh, uh, model where uh, finite element modeling is basically we can use for. So finite element modeling, we can predict the mechanical property, right? And next, I'll show you another slide, which will tell you define microstructural simulation, right? You can see using a phase field model. So as I told you, this mw2mech software is mostly for microstructure evolution. And here I am showing you few examples. So we have a group of in IIT Kanpur Material Science Engineering Department where we simulate different kind of microstructures, right, for alloys and other systems, right? So here are a few examples. You can see the first one is the effect of external magnetic field on spinular decomposition. So in this workshop, we'll Ms. Agarwal, just there is a call.
Yeah, I think you are not audible.
Oh, sorry. I think I am not audible, right? Yeah, now I am
Yeah,
audible.
now it is fine. Yes, yes.
Yes. So thank you. So I will start again. So the first figure you can see is the effect of external magnetic field on spinular decomposition, and I will go into more into spinular decomposition later, where we'll see this is a two-phase microstructure evolution, and one of the phases may be ferromagnetic, one of the phase may be paramagnetic in nature, and using an external magnetic field, we can align this magnetic field, these phases in particular directions, and we can change its properties, right? The second one you can see is the microstructure evolution of gamma prime precipitated in a gamma matrix using a multi-scale model. It's very similar to what we are showing you in this mw2mech. And this kind of microstructures are particularly important for turbine blade or turbine disc applications. This is a precipitation hardened alloy, which is a nickel-based superalloy. And most of the metallurgical systems are not pure metals, but alloys, and most of them are precipitation hardened alloys, like this Inconel-based superalloys, where you can see this cuboidal precipitate aligned in a particular direction, are responsible for the strengthening of this nickel-based superalloy, which is used for turbine blade application. If you think of an alloy which is used in say Boeing aircraft, right? It's aluminum alloy, right? But it's not pure aluminum. Aluminum is a lightweight metal, but we strengthen it with copper precipitation and many other components. So it is mostly the precipitation hardened alloy which are very important for applications. Say for you can see in this bottom left corner, this is the microstructure what we can see for aluminum alloy when we have a copper rich precipitates, right? There are say titanium alloys which are used for space applications, right? Which are very expensive. We cannot use them in normal aircraft or automobile applications. They're like titanium and titanium 6 aluminum 4 vanadium, this kind of alloys. But they are very lightweight and high strength alloys. But these are also precipitation hardened alloy, where alpha phase is alpha HCP phase is embedded in a BCC matrix, right? So these precipitation hardened alloy are very important. These are they form because of phase separation, and this mw2mech software targets one of such alloys. You can use defined alloy systems. You can actually simulate defined alloy systems which are precipitation hardened alloys, right? We can also use phase field model for microstructure evolution in thin films, how a whole growth in thin films occurs, pattern formation in thin film, island formation in thin film, the grain growth in thin film, because that is also a diffusion control process. These days, the high entropy alloy, right? High entropy alloy is also so high entropy alloy is uh, one of the thing of a hot topic these days, and I'll just try to minimize this. Okay. So microstructure evolution in eutectic material, and that can be also modeled using a phase field model. Okay. So next, I'll show you a multi-scale modeling approach. This is very important for our m2mech software, because here although you are the main thrust is on phase field model, but we are using a multi-scale model in overall, right? Where we are integrating the density functional theory, phase field model, and finite element model. So density functional theory, why we use? Because this we need several inputs from for this phase field model, like misfit strain, elastic constant, interfacial energies. All these calculations can be done using a density functional theory calculations or molecular dynamic simulations, mostly atomistic simulations, right? So their output will act as an input for a phase field model, which you can use to study the microstructure evolution, right? The second thing is the free energy, right? That gives free energy, which the thermodynamic input is needed for a phase field model, which is related to the solid solution model. And that is also I would like to discuss a little bit. So, so DFT part will be covered in the next lecture by Professor m2mech. And here there will show how to calculate the elastic constant using density functional theory, right? So the CalFat is a software package. You can say there are different software packages like ThermoCal, PanDat, which uses this CalFat approach, where you can use the gives free energy of a system, right? And this acts as the thermodynamic part for the phase field model, thermodynamic input for the phase field model. So if we know the binary, ternary, or a multi-component alloy, so from this software we can actually get. There are open source, open CalFat also, right? So for students, there is a version what you can download also. You can see how this, how we can extract the thermodynamic description of defined alloys, right? So, so at least for binary alloys, you can get easily, right? So those things you can extract and use in a phase field model. So this is the basic structure of our software. That is what we are discussing. Not the not about the graphical user interface, but the backend of the software, right? So so there we can calculate the misfit strain elastic constant using atomistic calculation. We can get the free energy from parameters from CalFat calculations, and use all these data as the output, as an input for a phase field model, which is used for microstructure evolution. Here you can see how the microstructure is evolving with time, right? It starts with very small precipitors having defined orientational variants, translational variants of gamma prime in a gamma matrix, right? So yellow is a gamma matrix and all other colors are gamma prime precipitors, but these are defined variants, right? And how they coarsen with time. So coarsen is a process where the larger particle grow at the expense of smaller particle. So this process is slightly detrimental for the property of a material. And we can actually, there are many ways we can stop this coarsening behavior. So it is very important to understand the coarsening of precipitate in a matrix. So once we have the output of the microstructure, how it evolves, we also need to know what will be the corresponding mechanical property of this material, right? So and these precipitates are in nanometer to micrometer region, so in the mesoscale regime, right? So next you can see there's once we simulate the microstructure using a phase field model, we can use the mechanical property can be predicted using a finite element model. And this will be demonstrated in the second demonstration today in the afternoon session, where the first, this figure you can see from the microstructure from phase field modeling. Then there's a finite element modeling, segmented and meshed microstructure. And finally, we can get the stress strain distribution. We can get the effective mechanical properties from these stress strain distributions, right? So this is the mostly the background for our software. So use CalFAT approach, density functional theory, and their output actually works as input for a phase field model. And then we use this phase field model for microstructure evolution. So in our software, you will mostly see this phase field model and this microstructure evolution in the m2mech software, right? And which can be integrated with the CalFAT data. That will also show how it is integrated to the CalFAT data. And these elastic constants will as an input. And once this is done in the second demonstration, you will see how you can predict the mechanical property once you have the microstructure. So next, so this microstructure prediction will be done using a OF, object-oriented finite element software tool for predicting effective properties from the microstructure. This is an open source software based on Python and C++ and can be integrated with other open source software and can be used to analyze two-dimensional and for 3D microstructures as well. Okay, so this is a fully capable standalone software and it's generated 2D to 3D mesh, can be exported to a commercial finite element softwares for elastoplastic and other nonlinear analysis. But most of these things will be discussed in the second demonstration. Okay, so I am skipping this part and we'll mostly look forward to the what is the phase field model and how it works, right? So this is the overall system. You can see these elastic parameters, interfacial properties are from atomistic simulation, gives free energy from the thermodynamic databases, which is part of the CalFAT calculation, atomistic mobility, diffusivity, which is the kinetic databases. So these together form the CalFAT approach, right? And this is a multi-scale model because the atomistic simulation is integrated with the phase field simulation. Then we have a quantitative phase field simulations where we can see spatial and temporal. Spatial and temporal means in space how it is evolving, and in temporal means with time how it is evolving, right? The microstructure is evolving with time, right? And once the microstructure is evolved, we can analyze this microstructure. So there will be some post-processing tool will be available along with this software where you can see the size, shape, and volume fraction of the constituent phases. Finally, we'll use this microstructure for computational tools for property prediction using OF2 software. So this is the overall diagram. You can see how this software works. Okay, so this is a overall this diagram, a flow chart depicting the complete and detailed process flow of m2mech, encompassing all essential steps. This is exactly related to the software, and there should be a folder structure overview of the m2mech, outlining organization and arrangement of directories. But I am not going into this. This will be covered in the first demonstration. So this is particularly related to the front end of the software, where you will use the software to run this phase field simulation. So even if you don't know what exactly equations you are solving, still using this GUI, you will be able to simulate this microstructure for a particular alloy system. Okay. So, but I am skipping this part because this will be covered by Albert in the first demonstration session in the afternoon. So in the afternoon, as I told you, there will be two demonstration sessions. One will be the front end of the software, and that will you will get an hands-on session for this front end of the software, the graphical user interface. So that is and there will be some post-processing tools also will be involved. That is the very important part. That's the demonstration one and the hands-on session, right? And the second demonstration will be related to the mechanical property prediction, which is related to this OF2 software. So now we know that. So till now, anyone has any question? So because this forms the basic background of the software, right? So if you have any question, you can ask me. Then I'll go to the next part of this lecture, where we'll discuss some examples of phase field modeling, microstructure evolution, and also we discuss a little bit about the solid solution model. So if anyone has any question or any doubt, please ask me. If not, then I'll go to the next slide, right? So now we'll discuss.
Is a question in the chat.
Yes. What is the question?
Can we check the microstructure evolution of ecliptic solution?
Afa?
Eutectic solution.
I don't get it. Is there in a chat box or somewhere this question is there?
Yes, in the chat window.
Chat. Yeah, I'll just check this chat. So hi, this is attendee, please rejoin. Sir, can we check the microstructure evolution in eutectic solutions? Yes, it is possible. The microstructures evolution of eutectic solution is a phase field model, although it is not integrated with this right now with this mw2mech, but we can always, because this is open source software, we can always add the modules here. And eutectic solutions are basically solutions where we have a transformation from one liquid to two solid phases. If it's a simple binary alloy, right, there may be ternary eutectics also or a multi-component, but if we can think of a simple binary eutectic alloys as the late-tin eutectics, say, right? So that kind of thing you can do easily. Because that is there you can see the solidification of the alloy, and that is also a diffusion control process. There is a liquid phase that is transforming into a solid to solid phases, right? I have shown you for the high entropy alloy in a slide that where we have all the examples, right? So I will go back quickly. Um,
Yes, sir.
So here you can see this is the eutectic solidification, right? In a high entropy alloy. Yes, tell me.
Yes, sir. In case of eutectic solution, it will be like can be like both the thing A and B can be solid in the room temperature, but when it reach to the eutectic composition, it become liquid at that and that the thing is like it is also actually kind of alloy. That's why I asked that if we start from A and B and go to that composition, it become liquid. And can you check that microstructure how it is actually evolved and how the A components actually evolved and how the B components and from our research we think that A and B it's not a like a rigid structure. It's somehow it may be the A rich and somehow it may be the B rich region also there.
Yes, yes. So in metallurgy, we do it in the opposite direction, means you have a liquid, right? And then if we cool it below the eutectic temperature, it solidifies into a two-phase microstructure, okay? Like you was telling that there are A and B components, you are hitting it above the eutectic temperature, it will be liquid. But it is more relevant when in our cases, we do the opposite, the solidification thing. But you can always do the melting also, right? That is also possible, okay? So here in this one, you can see that we have started the microstructure evolution during solidification, means you have a liquid of eutectic composition, right? In a phase diagram, you have a eutectic point, right? So if you have this composition and if you cool it below the eutectic point, it will solidify into A, say there are A and B atoms, right? So like you are telling, so there will be A rich and B rich phases, it will decompose, right? And it will form a lamellar kind of microstructure, right? And we study how these lamellar spacings will be with the undercooling, means how if you cool much below this eutectic temperature, there will be fine microstructure, what will be the, and if you are just below the eutectic temperature, there will be a coarser microstructure. Depending on different cooling, isothermal cooling or cooling rate, the microstructures will be defined, right? And this composition of this A rich and B rich phase will depend on the phase diagram, right? If you know the phase diagram, you can get that phase diagram data from the thermocalc or the calfed approach, and you can integrate with this μ2mech model, and you can simulate this kind of eutectic solidification. Okay, but this is a liquid to solid phase transformation. Right now, our this model is mostly for solid state phase transformation, right? But it follows similar model in our software, right? So phase field model is quite capable of studying the eutectic solidification, right? Where you have is eutectic and off eutectic also, right? Off eutectic means if you have slightly larger, higher composition or lower composition of the away from the eutectic point, right? So you are basically interested that what are these two phases, how the, so one will be A rich, one will be the B rich, right? And depends on the tie line, you can find out what will be these compositions, right, for the eutectic alloy. So am I able to answer your question, or you have something else to?
Yes, sir. You have answered my question that this program can be used, but I am interested mostly because when it is in a like eutectic composition, it is a room temperature liquid, and we are using it as a solvent. So, but still in the solvent also, there are some region. It's like what will be the A rich and what will be the B rich. I want to understand the solvent microstructure evolutions.
solved microstructure. I mean, are you from a chemistry background or?
Yes, yes, sir. Yes, sir.
Yes. Because I understand from some metallurgical point of view, because we are mostly interested in the opposite thing, where this
yeah, I
solidifies.
got it, but I think this software can be used because you are
Can be
starting
used,
from
can
the
be
same
used.
time.
Yes, can be used in this, but right now it is not incorporated, but we'll incorporate this because we have already this kind of model, and the background what equation you are solving is the similar equations, only you have to
Yes.
integrate the thermodynamic database with for this particular alloy. Okay, right,
Yes.
right. Okay. So I'll go to the next slide. Okay, yeah. So we can discuss later. Okay, if you need this thing to simulate. Okay, yeah. Thank you. What is your name?
Sir, my name is Tubai. I'm from NCL Pune.
Okay, thank you. So now we are going to a phase field model, right? Means what are the basics of phase field model? And so next half an hour, probably I'll cover this example of phase field model and also a little bit of solid solution model, right? So a phase field model is a diffuse interface model, right? When you have analytical models, right? These are mostly sharp interface model where there's an interface you need to track between the two phases. So we are mostly discussing about multi-component, multi-phase field model, where the alloy have defined means more than one element, and you have multiple phases involved, right? So, and for the simplicity, right now in this workshop, we are only working on a binary alloy. Binary alloy means two component alloy, and there are two phases, right? But it is also possible there are three phases are involved, like a eutectic solidification. You have three phases, like a liquid and two solid phases, right? So, this phase field model is called a diffuse interface model, and you can see there are some alpha particles in a beta matrix, right? And if you go through this interface between the alpha and beta, then the interface in the below you can see this is a diffuse interface with a region where basically the composition and other variables, the properties also changes in a diffuse manner, right? And this kind of change in composition and properties are captured using some field variables, right? And these field variables are phi RT. So this may be the field variables, maybe the composition, maybe the density. These are called conserved field variable. If you have a grain growth kind of thing, or a order disorder transformation that you have a magnetic domain, some of them are ordered, some of them are disordered, right? In that case, we use non-conserved field parameter. So what is a conserved field parameter? Because if there is an alloy we start with and it decomposes into two phases, and still the average composition of the alloy remains same, right? If you add all the composition and average it out, the composition remains same. Whereas for a non-conserved field variable, it's like a solidification is taking place from liquid to solid. In that case, all the liquid will ultimately transform into a solid phase. So one of the field variable will disappear from the system, right? So there are different kind of field variables with which we describe the microstructure. And this field variable basically is a continuous variable in a space, and they change in a diffuse pattern from when you go from one phase to the another phase through an interface, right? So then there is no variation within a phase, a large gradient at the interface, but this variation is always a smooth. And the microstructure evolution, how it works, when this interface basically moves, right? So if this interface basically moves, then alpha will grow inside the beta phase, right? So we basically track the evolution of these field variables, and if we plot them, we can get what is the microstructure evolution. So these conserved and non-conserved field variables, we generally solve two very basic equations, and there are some more complicated equation of variation of these equations. One is very similar to our diffusion equation. Many of you know the fixed second law, right? So where the driving force for atoms to diffuse, because these are all diffusive phase transformations, right? Whether it's a solidification or a solid state phase transformation, these are all diffusive phase transformation where there is a phase separation is occurring. If you have a and B atoms, this A and B rich phases forms, right, during phase separation, right? And there a diffusion is involved, right? So in the fixed law, what is the driving force for diffusion? This is the concentration gradient, right? And this concentration gradient basically drives the diffusion. So there we can see diffusion equation, which is like del C del T equal to M grad D grad square C, right? So the atom moves from higher concentration to lower concentration, right? Like a drop of ink, if when it is there in the water, it will diffuse into the water, right? So, but here we are solving an equation which is very similar to a diffusion equation, which is del C del T equal to M grad square mu. And this mu is the chemical potential. So when M is the atomic mobility, C is the composition, T is the time, right? And you can see here. And why we are using the chemical potential as the driving force? Because in many alloy systems, you will see the atoms can always go from higher concentration to lower concentration. But when, say, some mineral decomposition is happening, right, the atoms can move also from lower concentration to higher concentration. But in all the cases where it is moving from higher concentration to lower concentration or a lower concentration to higher concentration, the atom always moves down the chemical potential gradient. That means the atom moves from higher chemical potential to lower chemical potential. And this chemical potential you can calculate if you know the Gibbs free energy. That is why I told you it's very important to know the solid solution model. Right? So this mu total, this chemical potential is the variational derivative of the F is the free energy, Gibbs free energy, this Gibbs free energy. So this is a variational derivative with respect to composition. And there's a non-conserved field variable, like I told you, the order disorder transformation or a grain growth or solidification. You have a non-conserved order parameter also, which describes the microstructure, which is related to the Allen-Kahn equation, where eta is a non-conserved order parameter, L is the relaxation parameter, which is related to the kinetics, and F total is the free energy, right? So mu total can be in solid state phase transformation. So mu total, the chemical potential may have a chemical part which is coming from the bulk free energy. It may have other things like elastic parts, right? Because there are the lattice parameters which may be defined between defined phases. So elastic strain can be involved. There may be external stresses also. So generally in solid state phase transformation also we need to calculate the chemical potential due to elasticity, right? But if you want to calculate what is the effect of magnetic field, then there will be another mu magnetic, right? So the chemical potential will have several parts. Chemical part will always be there, and there will be elastic part. There will be other effects. If you have electric, magnetic, all these things can be incorporated so that you can see the effect of external fields and magnetic, electric, elastic, all these fields on microstructure evolution. So this is a very simple kinetic equation that I am showing you. And then this, as I told you, this F total it can be F chemical and F elastic. And F chemical, this bulk free energy and the gradient free energy. What is the bulk free energy that you get from the phase diagram and the free energy diagram? And gradient free energy is related to your interfacial energy. Is the part from the chemical part of the free energy. And whereas the elastic part of the free energy, you can see there is a, when we try to calculate the elastic energy, we basically have to solve the mechanical equilibrium equation. And we assume that at every diffusion time step, the system is in mechanical equilibrium. And mechanical equilibrium is much faster than diffusional process, right? Because the atom has to move a fraction of the atomic distance, right? So the elastic equilibrium is very fast. So we assume that at every diffusion time step, the system is in mechanical equilibrium. So that is why we solve a mechanical equilibrium equation to get the displacement field. From there, we can get the strain field. From there, we can get the stress field, and we can calculate the elastic energy of the system, and we can incorporate it in the total elastic energy of the system. So the bulk free energy part we can get from the thermocalc or the CalFAT approach. The gradient free energy, the interfacial energy, we can get either from literature or from atomistic simulation. The elastic part we need to calculate if we know the elastic constant from the atomistic simulation, misfit strain. Then by solving the mechanical equilibrium equation, we can get the elastic energy. So say, for example, to describe an NIAL system, we require one conserved order parameter composition and 3 non-conserved order parameters to describe 4 defined translational variants. Okay, so now we know how in a phase field model, how the microstructure is described, right? Now we'll go to few examples. I may not cover all of them right now, but at least the first one, the spinel decomposition, will cover. And I may show a little bit 1 or 2 microstructures from the other two, which is the microstructure evolution in thin film, microstructure evolution in superalloys. Okay. So because the mineral decomposition I wanted to cover, because in this demonstration or also in the afternoon session, the demonstration and the hands-on session, we have the background code is only for mineral decomposition for a binary alloy, a two-phase separation for a mineral decomposition. And that is why I just want to discuss few more things about the mineral decomposition. And it is very important not only for metallurgical system, but also for system where in a polymeric materials also you can have this kind of mineral decomposition takes place, right? In functional materials also. So like a ferromagnetic to paramagnetic, right? Phases, right? They are also, it is important. So we start with mineral decomposition. This is a kind of phase transformation, like a eutectic solidification or a precipitation. This is also a kind of phase separation where when an alloy basically decomposes into 2 or more phases, right? So you can see this is a temporal evolution of spinodal microstructure. You start with a homogeneous system where the composition is homogeneous everywhere, and it then decomposes into 2 phases, this orange and purple color, right? So you can see this is the decomposed to 2 phases, and these phases will coarsen with time. So the distribution of arrangement of these phases will basically, the volume fraction of these phases will basically important to understand the property of that particular alloy. And you can see initially there are incipient interfaces. You can not tell what is exactly the interfaces, but then the well-connected interfaces will form. And this is also known as a bicontinuous microstructure. If you can go through these purple phases, and go to the other side of the system or the orange phases, right? So this is a 50-50 kind of composition. So this is also known as bicontinuous microstructure. So this kind of microstructure is very, very important in different alloy systems. Say for magnetic system, right? One of the phase may be ferromagnetic embedded in a paramagnetic matrix, right? So it can form hard magnets because when you have small these ferromagnetic phase separated phases in a paramagnetic matrix is embedded, and then you align them in a particular direction, they can access a elongated single domains, right? So in magnetic material, hard magnets, this is very, very important. In different microstructures which we use for metallurgical systems, there also you use mineral decomposition for phase separation. It is also used in polymeric materials. Also, I am not very expert of polymeric materials, but there this mineral decomposition is observed. In glasses, say for borosilicate glass, right? This mineral decomposition is observed. Fine. This silica, you know, it's a very high temperature, above 1700 degrees centigrade it melts. But when this minerally decomposes, it decomposed into a boron-rich phase and silica-rich phase. And if you leach out the boron-rich phase, you will get a porous microstructure, which can be used for catalysis applications as well, right? So this kind of mineral decomposition is very, very important for defined metallurgical, polymeric system, glass system, in all these systems where the material decomposes into 2 defined phases. So what is the corresponding this phase diagram for a mineral decomposition? This phase diagram tells you the temperature versus composition diagram, right? And here we will say what are the equilibrium phases at defined composition temperature regime. And this, you can see, this is a phase diagram. I think many of you may be familiar, at least if you from metallurgical, mechanical, or chemistry background. I think you are familiar with some phase diagrams where we have this kind of diagrams where you can see at this what temperature and what composition rate, which phases are stable, right? Like if you take a composition, so right side is an A-rich phase, left side is the A-rich phase, or right side is a B-rich phase, right? These are 2 defined chemical elements, right? But if you mix them together, say at a composition of X0, so these are basically mole fraction, right? That's why it is written 1, right? So, and if you go to a T1 temperature, you will get a phase which is alpha, right? But if you go to T2 temperature, there will be a spinodal decomposition will take place, and this alpha will decompose into alpha 1 plus alpha 2. So if you take this X0 composition at a temperature T1, and then if you quench it at a temperature T2 and hold this alloy at this temperature, it will decompose into alpha 1 plus alpha 2, like that. Like the previous figure you have seen that it decomposes into orange and purple phases, right? So the alpha will decompose into alpha 1 plus alpha 2 phases, right? And this happens without nucleation and happens spontaneously, because if you see the corresponding free energy diagram, the Gibbs free energy diagram at temperature T2, you will see if you choose a composition, say inside the spinodal line, inside this, then a small fluctuation in composition basically decreases the Gibbs free energy, right? And that is why even a small thermal fluctuation causes a phase separation. Whereas if you outside this spinodal region, you can still get alpha 1 plus alpha 2, and this can happen through nucleation and growth. So these both are what the things are incorporated in our model. So you can either see spinodal decomposition or a precipitation, right? So if you go to a composition, say x dash 0, if you go from T1 temperature and if you quench it into a T2 temperature, the phase separation will take place by nucleation and growth mechanism, which is a precipitation mechanism. Because if there is a small fluctuation, it will not grow because the free energy is going to increase. But if there is a large fluctuation, it's a nucleation, then there will be a phase separation will occur, right? So typical free energy curves are double well free energy curves in case of spinodal decomposition or precipitation for this kind of phase separating process. So we'll also see when we'll extract the free energy for iron chromium or iron copper alloy, we will get similar free energy curve for those systems. So these are called double well free energy curve. So inside spinodal line, there will be no nucleation barrier. Outside spinodal line, in a two-phase region, there will be a nucleation growth. And you can see inside the spinodal, you can also see the uphill diffusion that I have talked about. So when the phases will decompose, the atoms can move from lower concentration to higher concentration as well. And this is this cannot be solved using a fixed law. That is why we use the equation, which is a Cahn-Hilliard equation that I showed you, which is a similar to a diffusion equation, right? Okay, so next, so this is a book where you can also see this textbook, the Porter and Sterling's book. You can see this kind of phase separation. You can read about it. Okay. So then this model description that we have already described. So this is what we have used the Cahn-Hilliard kind equation, where C is the composition, M is the atomic mobility, which is related to the diffusivity, F is the free energy, bulk free energy that I have shown in the previous slide, the double kind of potential. Kappa is related to the interfacial energy, and C is the gradient of the composition. So at the interface, you have a gradient in composition. So it will contribute to the interfacial energy. So if we solve this equation, this simple equation with proper initial and boundary condition, we can actually observe the spinodal decomposition. But what we need to know the free energy of the system. We need to know some data, the interfacial energy. We also need to know what is the atomic mobility or diffusivity parameter. So if you know the thermodynamic and kinetic parameter, we can actually observe this microstructure evolution during spinodal decomposition. So here we solve the partial differential equation, and the PDE provides the rule or path for the evolution of composition, and the PDE is solved numerically in a computer simulation, right? So this solution of this diffusion equation or the Cahn-Hilliard equation is the background of the m2mech software where it is running. It is solving this simple equation where we also need to integrate the bulk free energy from the CalFAT system and the diffusivity data also from the CalFAT approach we can get using DITRA, and this interfacial energy can be obtained from the literature or from atomistic simulations. So as I told you, this may be an elastic part as well, and the elastic part can be calculated using the mechanical equilibrium equation solving, or if it's the magnetic part, we can use the magnetic part of the chemical potential where you have to solve another equation which is called LLG equation. So the previous equation, you can see here you don't have any elastic part or the magnetic part, but if you want to solve what is the effect of elastic field, what is the effect of magnetic field, also you need to solve another two equations. One is the mechanical equilibrium equation for the elastic field. You need to solve LLG equation for the magnetic field. Okay, next I'll show you a typical phase diagram, which is we get from thermocalc or a CalFAT approach, and you can see there is a dome which is similar to what I have shown. You see this is the mole fraction of proper chromium, right? So this is the iron chromium system, and this is a dome phase diagram which is similar to what we have shown you, I have shown you here. Here it is very symmetric, but in the iron chromium, it will be slightly different, and there are phase separation into BCCA2 plus BCCA2. So this is the iron rich phase and a chromium rich phase, it can decompose, right? So, and this data can be extracted as 773 Kelvin. What will be the free energy? And that we can use for our input for our phase field models, right? So what is the CalFAD approach? Because we are talking all about the CalFAD approach where we get this free energy, right? So the CalFAD methods enables the calculations of phase diagram. Unless you know the phase diagram of a alloy system, you cannot simulate what will be the microstructure, right? So phase diagram and the free energy diagram. These are two the important thermodynamic data sets we need to simulate the microstructure evolution. The kinetic data set is also important because how quickly it is going towards the evolution, means what will be the time scale, that is important, because if you don't know the diffusivity value, you cannot tell what will be the effect of temperature, say, right? With increasing temperature, the diffusivity increases in an exponential manner, right? So those things we can get using the CalFAD approach. And this kind of softwares like a thermocal, the open CalFAD or Pandat, all these things have student versions also, where you can get defined databases like aluminum, silicon, iron, copper, nickel, titanium. All these databases you can get, which you can load in your this software in the calculation program. And then you can get graphs and tables. Graphs and tables means you can get the phase diagram, you can get the free energy diagram, and free energies as a function of compositions, right? So it is very important if you can learn this CalFAD approach, then you have a good understanding about the phase diagram and the free energy diagram of a system. And when you want to plot the free energy diagram, you can see this is a particular free energy diagram for iron chromium system, and this is without a magnetic part, where you can see again the free energy is a double well kind of potential, and when you incorporate the magnetic part, it will look like this. But this common tangent tells you that at these 2 points, these are the equilibrium compositions of these two defined phases. It is phase separating into 2 phases, right? So the common tangent, if you see, the chemical potential actually of A rich phase or iron in the alpha phase, and the beta phase will be same, and the chemical potential of the B is also same in the both the phases. Then they will be in equilibrium, and these are the equilibrium composition of these 2 phases that you can get from the free energy diagram. But this data is very important because if we feed this data as an input to a phase field model, we can see how the microstructure is evolving with time. So how we solve this differential equation? We solve this differential equation in Fourier space. We can use different numerical techniques like finite difference technique, finite element technique, all these things. But here we are using a partial differential equation solved in a Fourier space, because when we solve a microstructure evolution, we are basically solving a very small part of the microstructure, which is periodic in nature, right? And here, what is the advantage of Fourier space with solving? Because it's a 4th order equation, and it will become a 1st order equation in the Fourier space, and the numerical stability will be much higher, and we can solve it is with very easily, right? Using a smaller time step value. So the solution is very fast. And this is a semi-implicit Fourier spectral technique that also you can get in literature, which how we solving this differential equation in the background. So there are numerical why semi-implicit Fourier spectral. As I'm telling, there are maximum allowable time step, that delta T max, right? We are going in time, right? With time, how it is evolving. We can use a larger time step in this case, so the microstructure will evolve quickly in our computers. So that is why mostly we use this Fourier spectral scheme. So you can follow this chain and sense paper in computer physics communication, but that describes this numerical technique in detail, how we can solve a partial differential equation using Fourier transform technique. Then if you can see, these are the microstructure where you can see this is a no external field, this is a only elastic field or only magnetic field, and you can see with what is the effect of elastic field and a magnetic field on microstructure evolution, right? Okay, so there is something like AI ML these days people are using, artificial intelligence machine learning. So this μ2mech, you will get a set of data, right? The microstructure at defined composition and defined temperature. And this kind of data can be used for AI/ML applications as well, right? Because this, if you want to simulate large microstructure for an alloy system, it is time consuming, right? But with fewer number of calculation, machine learning techniques can be used for generalized time independent series, and it reduces significant reduction in time and computational power requirement. So data which we are generating from the m2mech means it is a set of microstructure or set of compositional information at different temperature, different time, that you can use as a data set, a training data set for a AI/ML model, like LSTM kind of model, like long short-term memory model. If you know, some of you, I am not discussing this thing. This is not part of the m2mech, but you can always use this data set as an input, a training set for a machine learning model. And then this machine learning model you can directly use for prediction of microstructure evolution quickly. Okay, next, I'll just quickly discuss, we don't have much time left. So I'll quickly discuss what is a solid solution model. And because that is what we are using in CalFAD, right? And these solid solution models are incorporated in our phase field model, right? So solid solution model can be ideal, regular, subregular solution model. And the CalFAD method, we use something called Rajdip and crystal polynomial, right? So once we get the composition of free energy versus diagrams for a binary phase diagram, we fit it into a polynomial equation, and that polynomial, that coefficients of polynomial, we use in our phase field model. So for finite solutions, there is a single component system. All phases have the same composition, but in alloys, however, composition is also variable. To understand the phase changes in alloys requires appreciation of how the Gibbs free energy of a given phase depends on composition as well as temperature and pressure. So in binary solutions, you can see XA plus XB equal to 1, right? So the mole fraction of A plus mole fraction of B equal to 1. So the Gibbs free energy of a binary solution of A and B atoms can be calculated from the free energies of pure A and pure B in the following way. So if you know the free energy as a function of XB, you also know as a function of XA, right? So the simplest possible Gibbs free energy, which is possible when you are have a mechanical mixture, means A atoms and B atoms are side by side you are keeping, then this is called a mechanical mixture. But when they are mixed together, there is an enthalpy of mixing and the entropy of mixing you also need to know, right? So when you have a mechanical mixture, the G1 is you can calculate XAGA plus XBGB. But when you are mixing these two different kind of atoms, that is what you are doing in alloys, right? Then if you mix XAGA and XCGB, then you can have XAGA plus XPGB, but you also have a delta G mix. That is the enthalpy and entropy of mixing will also be there, right? Because the enthalpy and entropy is also going to change in the system. And entropy is mostly the configuration entropy, right? Right now we discussed how the number of red balls can be arranged in a number of blue balls. That is the how many configurations are possible, right? So these two terms are very important. So if you know the enthalpy and entropy of mixing, then you can calculate what will be the free energy after mixing. So you can see from this figure, once these two defined kinds of atoms are mixed, if this GF or the Gibbs free energy for A atoms and this is the free energy of the B atom at a particular temperature, when you mix them together in a particular volume fraction, this free energy may decrease or increase, right? And it depends on what is the energy of mixing. And this energy of mixing, there are defined solution models. I am not discussing them. The ideal solution model, there are regular solution models where you have the enthalpy term is also there, and there may be sub-regular solution model. But here you can see at some cases, you can see this kind of double well potential also. And when you have pure A and pure B, but if you mix them together, you will get a free energy which will looks like a double well potential, which is very typical to a spiral decomposition, right? So this kind of free energy is important for today's workshop, and that is what we are going to discuss. And this kind of free energy you can obtain from CalFAD models, right? So finally, we have defined kind of models. You can read about it, the mechanical mixture, solid solution models for free energy of mixing, ideal solution, regular solution, sub-regular solution. But ultimately, we need to have more complicated polynomials which can fit to a free energy, which is also known as Rajdip crystal polynomial, where you have multi-component and multi-phase system, right? So not only for binary or ternary. So CalFAT basically we have this kind of polynomials where you can the mixing energy for gives free energy, right? So this you have to, because in 1 hour time or it's not possible to describe everything. So if you are interested, you can go back to a phase transformation book like Potter and Stirling book or any thermodynamic book to read about solid solution model. And then you can use the thermocalc to calculate what is the Gibbs free energy, because that is important to understand to run the diffusion equation, because the chemical potential is coming from the free energy. Okay, so and also in defined kind of phase diagram and how the free energy diagram looks like in a phase diagram, that is also very important. Say for this is a eutectic temperature, eutectic solidification, right? So if this is the eutectic point where the liquid is becoming alpha 1 plus alpha 2, right? Someone asked some question, right? What will be a free energy diagram at eutectic point? Eutectic point, you can see there will be a it is not here, but T1, T2, and T3, right? So just below the eutectic point where it will solidify, right? So say for T3 temperature, right, which is below the eutectic temperature, liquid is solidified into two phases, alpha 1 and alpha 2. So you can see that T3, the liquid phase free energy will be higher, while the solid phase free energy will be lower. That means at this temperature, the solid phase is more stable, and liquid will decompose into two solid phases, and their equilibrium composition will be dictated by these common tangent points, right? So this will be the composition of alpha 1 and alpha 2 when the liquid decompose into two solid phases, right? Okay, so I think I have covered many things in this last 1 hour. There were many more slides where we had some slides for our defined kind of systems where we use this kind of phase field simulation, like a brain growth in thin film, or for a nickel-based superalloy I had discussed. That can be also possible for using a phase field model, where you can simulate this kind of microstructure evolution like coarsening, and then we can use this microstructure to using OF2, you can predict the properties also. Okay, so with all these things, I thank you all for listening, and now it is over to Professor m2mech, who will discuss about the atomistic simulations. Okay, thank you. So if you have any question, you can ask me. Is there anything in the chat box, or anyone can ask me a question? You can also have a question and answer session at the evening, in the evening. So that time also you can ask many things about the phase field model, how it is incorporated. In the afternoon section during demonstration, it will be more clear when we'll demonstrate how this mineral decomposition we can simulate using a m2mech software. Okay, thank you everyone.